Okay, good afternoon, class. In the previous discussions, we are discussing regarding the modeling of data flow. Okay, in that we have stopped at the discussion of assign statement, right? So assign, so it is just like you are willing to assign some value to some other variable. For that purpose, we are using this assign statement. That assign, for that we are using assign space e, the variable what. We want to assign some value to that variable, so that variable has to be mentioned there. Assign e is equal to a double and b, right? So we have different operands for single and symbol and the double and symbol. That thing we'll see in the table, upcoming tables, right? So f is equal to c and d, right? And g1 is equal to e or b. R is that is the symbol for r, right? E or f, right? So G is equal to not of G1. So that is equal to is used here as an assign, right? Assign statement. So in our total concept of coding is always we try to reduce the number of lines of the code, right? So we used to club different number of statements into a single statement. But for understanding, we should know what is the meaning of that particular statement. And if we want to expand that particular statement, we have to expand it to 3 or 4 lines, a single line. Or and when we after knowing that in detail, we can use a single line for instead of 4 or 5 lines. That is the concept of the coding, right? Okay. So why we are doing like that? If there are more number of lines, it takes more amount of time to execute actually. Okay. Mm. If it is executing sequentially means it will be taking more amount of time. If it is executed parallelly means so total program will be executed with some amount of time. Parallelly in the sense all the lines will be executed at a time, right? So see here. So this is the AOI. This is the symbol of AOI, right? AOI. I think for you. Okay. You can see. So this is the AOI. This is the AOI gate. The first for the same thing you have written the code for it at a single statement and writing in 2 lines. First one is writing everything in a single line. Second one you can see second part is just writing in 2 lines. Now you can see the third part. It is writing in the 4 lines. So everywhere we can either expand or we can contrast the code, right? So you can see here, this is the bitwise OR operation. This is the bitwise negotiation operator. This symbol. Okay, we have used those symbols, right? So combining assignment and meta declaration. Okay, so we can combine. So just now we have discussed regarding the assignment statement, right? And we are always sometimes we will be using the meta declarations. So you see here, we can combine the both. While C, that is nothing but it is net declaration. So this assign C is equal to A and B. It is an assignment statement. Now we can combine the both as while C is equal to A and B. While C is equal to A and B, that is you are combining both the assign statement and as well as the net declaration. Net declaration that while is equal to C. Right. This is also possible in the Verilog HDL, right? So you can see here in the previous three parts, we have given only this particular statement. If it is written in the part of a, as part of the total program, it will be like this. This is the main module. For the main module, we have to write the test bench. Okay. So this is where we are using the four set of statements for the same. Instead of having this one in single line, we are using here in the four lines. Same type of code. So it seems to be like this. The synthesizing circuit seems to be like this for the overall. So we have two NAND gates, sorry, two AND gates and two OR gates. Actually, it is an XNOR. So XNOR is nothing but just like an XOR with an inverter, right? So here you can see continuous assignments and strengths. So we should know the strength, strong 0, strong 1. These strengths we have seen in the table in the previous discussions of the class, right? So we have pull 1, pull 0, strong 1, strong 0, weak 1, weak 0. Like this, we have different types of strengths of a particular signals. So even we also had this table showing that which is more stronger signal, right? So it will be helping us to decide the output value. Why we are using this strengths? These strengths are used to identify what should be the output. Whether it has to be, see here, it is pull one and strong zero for the G. Okay, so when it is one, that means the value of G. When the value of G is one, it is pull one. That means the most strongest one. So next to it is strong zero. Just this is highly stronger than this zero, right? So not only that, when we are willing to write the program, sometimes we wantedly require some amount of delay in the programs. Why? Why? Because a single circuit may have different parts. A single circuit may have what we say, a single circuit may have different number of components. One component will be executing very much faster and another component will be executing a little bit slower. So that the outputs of the both parts of the devices has to reach one particular node. After reaching, not we can say not it is not node, it is another gate, right? So one will be occurring earlier and another one will be occurring late, right? So in that cases, to make the signal which is coming faster to sync with the other signal which is coming late, we require wantedly some amount of delay. Okay, that's the reason why we are willing to add this particular amount of delay wantedly, right? So this is continuous assignments and delays, right? You can see we have a wire. These are the nets. A, B, C are three nets, wire nets, and assign. Assign is the assign statement, right? Where between A and B there is some logical AND operation, and it will be performing the logical AND operation. It will be sent to C after two units of delay. Do you get now? So A will be performing, A will be having one value and B is having another value that will be stored to, that will be assigned to C after delay of 2 units time, right? Okay, so it seems to be like this for the waveforms. So in the previous discussion, we have explained detailedly regarding this. A is changing at 2 nanoseconds and 5 nanoseconds, 8, 9, like this. B is changing at 2 nanoseconds, 6, 8 nanoseconds, 30 nanoseconds, like this, right? So that means here we are continuously using here. We are mentioning A and B as wire, and instead of we are combining the wire and the assignment, assign statements here. Wire slash 2 C is equal to A and B. That means in the single statement you can see what we are having. We are having a wire statement, assign statement, and also the delay. Totally three statements in a single statement. You can see three works in single statement. So that is we are we are compressing the code. We are reducing the code. So this is the assignment to vectors. You can see concentration of vectors. So sorry, concatenation of the vectors. You can see concatenation means if A is of 8 bits and B is of 4 bit and C is of a scalar, we can combine by using this type of bracket here, right? We can combine with the help of this type of bracket by separating with the help of some commas, right? And not only that, total A is of 8 bits and total B is of 4 bits. Or we can also do, instead of a total vector, we can take some part of the vector and also we can concatenate it. That is the thing here. A is of 8 bit means that means 8 A7 to 0 it will be there. But we want to take a part of A7 to 4, only the 4 bits. 7, 6, 5, 4. So only 4 bits of A, it is used as an MSB. Okay, here MSB position, right? And the rest part is from B2 to 0, that is only 3 bits. B of 2, B of 1 and B of 0. All these 3 bits and these 4 bits, totally it is 7 bits, right? For concatenation we are using this brackets, right? This braces we are using. Okay, and we are separating with the help of comma, and here we can use both the total vector or else only part of the vectors when we are combining that. So it with complete adders. Okay, here you can see A is of 7 bit, A is 7 bit and B is 7 bit. The output C is also, sorry, A is 8 bit and B is 8 bit, and output is also a C is also a 8 bit. But we will have some carry, right? Sometimes we may have carry that also has to be stored, that can be stored in CC0. So this is CCI is the carry input. Sometimes the output what we have got, that carry may also be fed as an input to the some other circuit. So you see here you are assigning the values A plus B plus CCI, total thing you are adding, and that things are stored in this fashion, right? The most significant bit what you get, the most significant bit what you get, it is stored in CC0, and the other rest all other 8 bits will be stored in C, right? So that is the value of assign statement. So not only that, instead of having a repetition, instead of having a repetition, writing same thing multiple number of times, instead of that we can have some other type of coding. You can see here, instead of writing like this, p comma p, here we are writing 2 times of p. here 2 times of p comma q. The meaning of this is the short form, right? This is the short form, but we should know what's the meaning of it also, right? So actually, instead of writing like this in the code, instead of writing like this in the code, we are writing like this. Okay. So assign ground is equal to supply of 0. So for the ground we are giving a supply of 0, right? And we are also giving here, as we are assigning p is equal to 8 times of ground, right? 8 times of ground. So this is, you can also see here, a comma 3 times of 2 times of b comma c comma d. That means b comma c comma d is written 2 times with the combination of d, and the total thing will be written in the 3 times, right? So here you can see BC BCD. This is the one. This is one part. This is BC BCD. This is another part. This is BC BCD. This is another part. So for the total thing we have A here. For the total thing we have A. This total thing is concatenated. See, instead of writing this much number of bits, that means such a long statement, we are writing it in a less length or statement, which will be helping us while executing the program. So we have some operators also. These operators are similar to that of our C language. So such as unary operators. Unary operators means we will be having a single operand. Unary operator means we will be having a single operand. So that means we are using some symbol, either plus or minus, for example, in front of a single single variable. So generally we will be using a positive plus or negative symbol. So by using a negative, that means a minus symbol, so you can see plus and minus we are used before some integers or real numbers. Okay, to change its sign. Okay, and by using minus symbol, it is nothing but a negative symbol, right? That means we are changing that number into a negative number, right? So we have some table, right? Like see table 6.1 here, where this will be used. These symbols, this or this will be used. Generally, we will be using. We will not be using this. This will be used only for scalars. I can use this for both. So I will be using this type of symbol only. It will be helpful for both the scalars and vectors for negotiations. So reduction or nor, like this reduction x nor, unary operators and their symbols you have seen here, right? So not only this, we also have the binary operators. So these binary operators will be taking two operands. Here we will be having only one operand. Okay. So the binary operators are grouped into type categories and discussed separately. Okay. So you can denote, you can use this arithmetic operators, treat both the operands and also numbers, right? So you can see arithmetic operators. So these are the arithmetic operands. We use this star for multiplication purpose, this backslash for the division, where we'll get a denominator. Okay. So that means division. Just by writing this backslash, we'll be getting coefficient. Okay, only the coefficient will be taken. The result is x. The result is x if the denominator is 0, right? So modulus, it will be giving the remainder. We will be taking the remainder. A percentage. The symbol what we are using here is for modulus is percentage, where we will be taking the remainder as our result. So for the division, you can see here we are using backslash. General, that means that is the coefficient we have to take. The denominator is 0, then we take the value of x as the coefficient what we get there, right? Yeah, some observations over those. So generally in the integer division, the fractional part of the result is truncated or ignored. Truncated means you don't consider that, you remove that fractional part in the integer divisions, right? So we also have some logical operators and relational operators also. So in the logical operators, we'll be using true for true. We'll be using 1, and for false, we'll be using 0. You can also see the table here, 6.4. So you can see here. You can see here. What's the meaning of this percentage and not using up the percentage? You can see 15 percentage 5 means percentage means it has to take the result, right? Result of the operation. Result of the operation is 0, right? That means it is taking only the remainder. Sorry, it is taking only the remainder. 15 percentage 5 means it is taking remainder as 0. So here you can see 14 percentage 5 means here it is 4. The coefficient, we are getting a coefficient of 4. It is if it is 15 means we have a coefficient of 3 and a remainder as 0. But it is not the case here. Okay, you can recollect once again. So division for backslash will be taking the, you see here, for the division we have two types. One for the division, this is for the getting the coefficient. This is to get the reminders, right? So not only that, we also have some relational operators, that is double and symbols, okay, binary logical operations, and also the or symbols. Not only that, we also have this relational operators, greater than or lesser than or greater than or equal to or lesser than or equal to. Okay, we also have these relational operators, and not only this, we also have this equality operator. In the equality operator, if we compare the two things, and if both are equal, then we will be giving the result as 1. If this, since both are same, and if not, we will be giving result as 0. That means the both are not equal. Because logical operations also we have this. So not only this, we also have bitwise logical operators also. These are the bitwise logical. So this is equality operators. So double equal to, it compares the two consecutive equal signs. Compares to consecutive equal signs. If the two operands are equal bit by bit, then the result will be 1. Yes, the result will be 0 there. If any of the operands, if any of the operand bits we have two operands. If any of them is having a bit either as x or 0, either as x or 0, at that particular point of time the result will be x only. X means just we are ignoring, right? We are ignoring it. So not only that, equal to as we have equal to, we will also have the not equal to symbol also. So what is this example? So here we have to find the difference between double equal and triple equal. So here it is comparing, and in the bits of the operands, that means the operand variables, if we have z or x bits, the result is only x. But when we are mentioning these symbols, that means triple equal and also not of double equal, it is like that. That means we don't want to see the result as x. We want to conclude the result either as 0 or 1. That's it. Okay. If the two operands match and bit by bit basis, the result is true, means it will be giving 1, else it is giving 0. That means we don't get a value of x at any time. In the similar fashion, if both are bitwise not equal, then we will have 1, and if it is same, we will be getting 0. So the symbol compression, you can see the operand bits can be 0, 1, and next. If the two operands does not match bit by bitwise, the result is 1. If it does not match only, it is 1, else it is 0. Generally everyone is to think for this. If doesn't match, we are saying that it is not equal. So if it is not equal only, we have to give the result as 1. Okay. If it is not equal, someone is to give it as a result as 0. Okay, it is not that one. If they both are not equal, only we have to give the yes, they are not equal. That means it is true. Else it is false. So this is the operators truth table. So with logical operators and their symbols you can see here. With logical operators in the sense and operation or operation x or x nor like that. So these are the truth tables. Okay, you know what are those? Okay, just with the discussion what we had, you can say for an AND gate, when input 0 is input 1 is 0 and input 2 is 0, for that we are getting 0. Here 0, one input is 0 and another input is 1, we are getting 0. So one input is 0 and another input is x, that means we don't know what it is. So for that also we are clearly mentioning it as 0. Why? Because this AND gate, since it is AND gate, we know clearly that when there is 1 1 only, it will be becoming 1. So that is 0 and unknown, so it is 0 only. If it is 1, so this and, since it is and, actually it has to be 1 here. It is 1 here, it is 0 here. This is 1 0. 1 0 can when it is an AND gate, 1 0 can't produce a 1 here, right? It is producing a 0 here and it is an 1 here. For 1 and 1 it is 1. So for 1 and x, it is unknown, right? We can't say, it depends upon the value what we use here. If it is 0, it will be 0. If it is 1, it will be 1, since it is 1 here. So we can't predict for some of the cases. So if it is x, we don't know what is the value it is here, but it's an AND gate. Since it is 0, it has to be 0. If it is, we don't, even though we don't know the value here 1 or 0, but the other value here it is 1. So if it is 1, then it will be 1. If it is 0, so if it is 0, it will be definitely 0. So that's the reason whatever the value what we give here, that will be coming here. So not only this, we have to compare with the unknown values also. Okay. So we also have the shift operations, that is right shift, left shift. They the operator executes leftward shift operation, while not only that, while this symbol will be executed for the right shift operation. So when we want to shift the data, you have to mention for how many rotations it has to go, or else for how many bits you have to shift. The thing has to be mentioned, right? Ternary operators means which we can where we can use two operators on three operands. Okay, two operators on three operands is nothing but the ternary operator. If A is true, if A is true, the value should be B. That means the B statement has to be executed. If A is false, the C statement has to be executed. That is the meaning of this ternary operators. This may be a part of the program or some other separate program, whatever it may be. If A is true, this is the meaning. Capital A, question mark, B, colon, C means if A is true, the B set of statements has to be executed. If A is false, C set of statements has to be executed, right? So here we are using the operators question mark on the column. We can't say this is column, this is semicolon. We can say this is column only. The conditional. This conditional operators you can see here. You can see the right shift. You can see the right shift operators. A is shifted. A is shifted right by b small b number of bits. A is shifted left by small b number of bits. Do you get now? Shifting right and shifting left. The small b indicates the number of bits it has to be shifted. So this is the one. So this we have many number of further modifications to the same conditional ternary operators. S and y is equal to w question mark x colon z. That means y will be given a value if w is correct. If w statement is correct, the value of x will be going to the y. If the value of if w is not correct, the z values has to go to y. The same thing will be here in the explanation. If the bit w is true and y is assigned the value of x, this is if the okay, right, that is if w is false, y is assigned the value of z. So not only that, the flag, if you want to assign some value to the flag, so address 1, if the address 1 is equal to address 2, then the value, that means 1 1 will be assigned to flag. What is this meaning? It is its value is 1. It's a binary 1. It's a 1 bit binary. Sorry, sorry. This is 1 bit binary. This indicates 1 bit binary, and what the value is? The value is 1. This is 1 bit binary, and its value is 0. Right. So we also have this 0 flags where we wantedly give some value of zeros, right? So you can see, or you can go through these total things. So if you want to evaluate, you have to evaluate from the innermost conditional operation to the outermost conditional operators. So you have to evaluate from the right to the left for these ternary operators. So So these are the examples for the ternary operators. So that's it.